Hi there! In this video, we're gonna learn another classification method that is what we call the KNN or the K nearest neighbor. This KNN is actually said to be quite different from other learning methods because unlike the previous learning methods, KNN does not build a model from the training data. So given the test instance D, for example, or the new instance to be classified, we actually define K neighborhood P as the K nearest neighbors of D. So in this case, as you can see, there are 1, 2, 3, 4, 5, 6. 6, which is the value of K as the total number of the nearest neighbors of the new instance D here. So what we can do is to count the number N of training instances in P. Those are the number of nearest neighbor that belong to class CJ. So in this case, we can see at least 3 classes, color the screen, the red and the black. But as you can see, the value of K as 1, 2, 3, 4, 5, and 6, there are 2 possible class or categories which this new instance D can be classified to. So we can estimate the probability of C sub J given D as N given K. So in this case, no training is needed. And the classification time is actually just linear in training set size for each test case. That means that, why is this so? Because as you can take a look at this, we have to get actually the similarity distance between this D, new instance D, to each of the elements that you can find in the entire data set. So the motivation here is that classification tasks can be very difficult when you feature or when the features and target classes are numerous, complicated, or extremely difficult to understand. So in those scenarios where the items of similar class type tend to be homogeneous, nearest neighbor classifying method are said to be well suited because assigning unlabeled examples to most similar labeled examples would be fairly easy. And actually, such classification methods can help us to understand the story behind the complicated case studies. And this is because machine learning methods generally have no distribution assumptions. However, this non-parametric manner makes the methods rely heavily on large and representative training data set. So here is actually the KNN algorithm, where K is usually chosen empirically via a validation set or cross-validation by trying a range of K values. Later on, we will be tackling or mentioning how K is being identified or determined in most cases. So we are talking about the distance function. Distance function is actually crucial, but it actually depends on the application. We are, by the way, dealing with the distance similarity in this case. So the KNN algorithm actually involves the following steps. We have here 4 steps, and as you can see, this is quite familiar with you because we already have used this in the previous classification methods, such as the decision tree and the naive Bayes. So let's just might as well we can make use of this. That is under the assumption that each data point or case or instance already being classified to which category or group or class it does belong. So in this case, if you can remember, this belongs to group 1. In this case, we label the Setosa in versicolor and in Virginica. But in unsupervised learning, given the data points or data set, there can be a technique that can be used in grouping or classifying the data points. For example, we have this what we call the principal component analysis, or PCA, which we will be also tackling as we go along with this coursework. And just understand by now that this is under the assumption that each of these data points has been already grouped in a certain categories or classes. And what we can do is, what if there's another test set or instance? In this case, in our previous slide, we call it D, so that the problem now is, the task now is to determine which category or class will this new instance belong. So first step is, for purposes of demonstration, we create a training data set that has classified examples labeled by nominal variables or the different features in ordinal or numerical variables. So we take a look at this example of the Fisher iris, and then next is actually to create a test data. So granting this is now our D, a new instance to be classified that contains unlabeled examples with similar features as the training data. So looking at the training data here, we have this test data set, and then which is somehow having features that are similar to this training data. So by inspection, we can see that it's somehow similar to versicolor, or this group over here. So the third step is, of course, given a predetermined number k, because as we have mentioned earlier, k is the value where we consider as, or we set as, the number of the nearest neighbor of a particular instance to be classified. So again, given a predetermined number k, we match each test record with k training records that are nearest in similarity. What does this mean? So we have here the three subset or sub-steps here that somehow will explain further how KNN algorithm works. So we define D, big D here, as our data set, training set, and the data set having different data points, as you can see here. And then we have here D, small d, as our new instance here, and the K as our certain value or the number that we can consider as the nearest neighbor of this new instance, D. So what we can do is we compute the distance between this D here and every example in D. So these are the examples in our data set D, and I just randomly connected here a broken line from this point, the distance, the instance D here, and then we get the distance between this and this and another point, and this also to another point, until we finish all of each, or computing the distance of this new instance to each of this sample in D. So next is to choose the K examples. Choose the K examples in D that are nearest to this new instance D, as you can see here. And we denote that as the set by P, which is the improper subset of the entire data set D. So this part here is actually our P. And so we assume that we place K value as 4. That means we would like to get the 4 nearest neighbor of this new instance D. So then we assign D, we assign this D, the class that is most frequent class in P. So notice in the previous slides that the most frequent class of the 4 neighbors, nearest neighbors, they actually belong to a class that is colored green. And so we classify this new instance as our versicolor, or the majority class, as we say. Okay, so that is based on the 4 nearest neighbors. So that is the last step, that is assigning the class that contains the majority of the K training records to the test record. So what if we have another instance or new instance to be classified, to determine whether it belongs to this group, or to this group. So here, of course, given the predetermined number K again, we match each test record with K training records that are nearest in similarity. Again, similarly, we compute the distance between this new instance to each of these elements in our dataset D. And then we choose the K examples. So assuming we are to make use of the value of K, which is equal to 12. And the task here is, what if K is equal to 12 and the new instance here is between two classes or categories, as what you can see here. So the problem now is, which of these two categories will this new instance be classified? So what we can do is, of course, assign D, same thing, assign this D here to a class that is most frequent, or most frequent class in P. So this is actually our P with 12 nearest neighbor. So if K is equal to 12 and the new instance is between two or more classes, so in this example, we have 8 nearest neighbors are actually red and the 4 nearest neighbors are green. So it's evident that, of course, basis for classifying, we simply choose the class that gets the most votes. And in this case, it's the red color, or the setosa. This means that the new instance belongs to this class. Okay, so those are the steps that the KNN algorithm actually follows in classifying a particular new instance, in this case the D that we have mentioned earlier. So I will be showing to you another simulation that can be found in codeopen.io, that's given by the reference that we have identified in the first slide of this video, where we can actually explore later on. But for purposes of demonstration, just a quick demonstration, let me just open this URL where we set here K is equal to 3. That means that we get the 3 nearest neighbor of a particular new instance, and that it actually defines or determine which category will this new instance belong. So if you navigate here, notice that the big circle here, that is said to be our new instance to be classified. And since we define 3, we can take a look at the blue colors here, the blue, or the data points or elements in dataset. We have the blue and the orange. So what does this mean? So as we have mentioned, to decide which category will it belong, we have to consider the category with the most votes. So in this case, it may be near to the orange category or class, but the blue here has the most votes, and so the new instance is actually classified with blue category. If you take a look at this one, still 3, so still in blue. But if we have, what if the new instance is somehow similar to these data points? So that's why it has here orange. That means that the new distance belongs to orange category. So I hope it's clear to you. So you can move on here, move to this. It keeps on changing because it depends on the similarity distance. That's how KNN works. Okay. So to go back here, you might as well take a look at the live demonstration as I've shown earlier. It is actually an app that would automatically compute the neighborhood size and the corresponding label, or that is in the by means of color, that represents which category it does belong. So since we talk about the similarity distance, this distance function, the distance function and the dummy coding are actually involved here. So the question would be how to measure the similarity between records. So that's the question, right? So we can actually measure the similarity as the geometric distance between the two records or the two instances. This is what we mentioned earlier. The two instance that we are referring to is the features of the new instance and the features of the other record or other point that is found in the dataset. That's why it's linear, because we get or we compute the similarity distance of the new instance and then distance from the new instance or record to each of the element in dataset. So there are many distance functions to choose from. However, traditionally, we can use Euclidean distance as our distance function. So how do we do that? So if we use a line to link the two dots created by the test record, if you can remember our small d, and the training record in n-dimensional space, meaning each of the points in our dataset. The length of the line is the Euclidean distance. Suppose that we have A, B, both have n features. For example, we have two features, like as we have seen earlier, we only have two features represented in x and y axis. If you remember our previous demo, we have the petal length and the petal width with coordinates, for example, A1 and A2. But in here, we have more than two features. That's why we have A1, A2 to A10, and B1, B2 to BN. Sorry, that's BN. So a simple Euclidean distance could be defined by the square root of A1 minus B1 square plus A2 minus B2 square, and so on and so forth. So think of this, for easy understanding, think of this as two data points. For example, if we go back here, this point and this point, we get the distance from here to this point. So somehow this is 2.1 and this is 2.3. We get the difference between these two and square it plus our y here, this minus this one, and we take the square root as being given in Euclidean distance, and we get the distance between that 2 points, and that serves as our basis to whether or not that can be considered as part of our P in determining the nearest neighbor of a certain new data or instance to be classified. So still in distance function and dummy coding, when we have nominal features, it requires a little trick to apply the Euclidean distance formula. For example, if it's like we have a nominal features, like categorically it will be either male or female, but we can actually make use of dummy variable in which that dummy variable would equal to 1 when we have feature and 0 otherwise, as we can see in these two examples. So this actually allows only binary expressions. If we have multiple nominal categories, just make each one as a dummy variable and apply the Euclidean distance. So question is that what are the ways or the methods or approaches to determine our K then? Because in our early example, we set K that is equal to, take a look at here, 4, and then we also have used here K is equal to 12. So when do we decide whether it's 4 or whether it's 12? or whether it's any other variable value of k. So it's very important to consider this because the parameter k could be neither too large or too small. If the value of k is too large, the test record tends to be classified as the most popular class, right, in the training records rather than the most similar class. So, but on the other hand, if the k is too small, outliers or noisy data like mislabeling the training data might actually lead to errors in prediction, and that would actually affect our accuracy or the performance measure that we are looking forward. For example, the performance measure like specificity, sensitivity, the accuracy, precision and recall, and so on and so forth. So a common practice is that to calculate the square root of the number of training examples and use the number as k. So, for example, in the previous example, we have 150 as the data set size. We get the square root of it, and it's like approximately around 12. And so we use the value 12 for our k in the previous slide that we have shown. So a more robust way would be to choose several k's and select the one with best classifying performance. So there are some other approaches or strategies for us to make sure that accuracy and other performance measures will not be sacrificed. Okay, that's all for this video, and I hope you have understood the concept of KNN and how k nearest neighbor algorithm work. So that's all. Thank you.